meeting is now being recorded.
So we're lucky today to have Sebastien Philippe from Princeton University. He works in Alex Glazer's group there, talking about some work they've been doing on applying zero-knowledge protocols to warhead verification. So, Sebastien.
Thank you, David, and thank you for the opportunity to talk today. It's my first talk, I must say, without seeing my audience, so we'll see how that goes. David gave me the opportunity to talk about our zero-knowledge project today, and I'm very glad to do so, and I'm also very happy because we recently have this project reach another stage where we actually did experiments that were worked out, and so today I would like to talk to you about that also. Before I dive into today's topic, which is the application of a cryptographic concept to nuclear warhead verification, I'd like to just to say a little word about the other projects that we do at the Nuclear Futures Lab in Princeton, and also explain to you, if you go to our web page, why do we have three letters acronyms? So because we are cool people, sometimes we always try to find, design design ID to present our work. So here are the projects. They all have three letters because that's kind of like corresponding to place we can travel to. They're all not too far away from each other in the sense that we work a lot on nuclear verification and trying to develop new ideas to verify futures treaty or to try to improve current ones. So we have a nice project on zero knowledge, on virtual reality, open source softwares, nuclear archaeology. So I will let you try our website if you want to learn more about that. So today we'll talk about our zero knowledge warhead verification, and here's our project team at the moment. We have on the left pictures Alex Glazer, my advisor, that a lot of you know. Then I'm the one opening up the warheads, and it's glowing inside. I can't tell you why, and you will not learn why during this talk. Also, it's a zero knowledge talk. Next comes Rob Galston, who is the director at PPPL, the Princeton Plasma Physics Laboratory, for over 10 years, and has joined our team many years ago now. Then Boaz Barak at Harvard, that was one of the co-author and early group member that I've worked on the idea of applying zero-knowledge proofs to nuclear warhead verification with Alex and Rob, and they all published a paper in 2014 in Nature that that's really, I think, had a very positive impact on the ARMS control community and the verification community in general. And last we have Francesco Derico from Yale, who is a specialist in nuclear physics, and that builds fantastic detectors that we will talk about. That today also, because we use those detectors in our approach to try to confirm the authenticity of nuclear weapons. So I will start briefly by giving you a background, some background information and motivation of why we have been working on this project. Then we'll talk about the topic of zero knowledge verification. We'll discuss how we went from thinking about having this idea and thinking about the concept to going down to building an experiment that could provide that back actually, back up the theory so far. So I'll show you some experimental results, and then I'll talk about where we're going next with this project. So this is a famous, I would say, graph that many of us know, which is the worldwide nuclear weapon inventory from 1945 to 2015 here in this case, and how that global stockpile evolved with time. And here what I am interested to talk about is the distinction of where those warheads are today in 2015 to 2016. Some of them are deployed on strategic delivery vehicles. Some are stored in kind of like reserve stockpiles as like spare parts or warheads that could be uploaded on delivery vehicles. Others are tactical nuclear weapons, and some finally in the third category are warheads that are waiting to be dismantled, so old models that are no longer in the active stockpile. If we look at the number, we see that currently only roughly 3,200 warheads are somehow accounted under international treaties, and there's only one actually. It's the bilateral treaty between the U.S. and Russia, New START. But most of them, roughly 6,000 are in reserve and unaccounted for, and another 5,500 also in the dimensional queue and unaccounted for. And when I say unaccounted for, I mean that there is no treaty that try to govern those objects. There's no treaty that try to verify that those warheads being dismantled are properly being scrapped. There's nothing that accounts for, warheads in stockpile. And of course, there's no treaty today that bounds any of the other nuclear weapon states towards, either limitations of their armament or even reduction of their armaments and so on. So our project basically tries to develop, techniques and technical techniques and inspection protocols, I must say, so that we can eventually, if a nuclear weapon state agrees to it, move on to a regime of arms reduction, where we will try to account for all the nuclear weapons, wherever they are stationed, deployed, in reserve of being dismantled. But the point of including warheads in a verification regime is not necessarily super easy. It brings new challenges that never really happened before. And three quick examples. For example, if you wanted to include warheads in a multilateral arms reduction treaty, then you may want to be able to verify numerical limits of items that are declared as nuclear weapons. You may also want that items that are declared to be nuclear weapons to be authentified as real and not as spoof, for example. So, you can go from a bag of rocks to a bag of rocks with some uranium and plutonium to uranium and plutonium but no explosives. So we can think about all kind of ways to spoof a system that would seek to authenticate such warheads. And finally, we want also to establish confidence that there are no secret stash anywhere, basically undeclared stocks or secret productions of warheads going on, if you were to try to limit their number or try to reduce their number. So this project, the Zero Knowledge project, is really focusing on point number 2 here, which is confirming the authenticity of nuclear weapons. We know that nuclear weapons particular signatures. We know that from various exercises that were going on at the late 80s and also in the 90s and early 2000s. But the problem with this is that a lot of the signatures that you expect to see from nuclear weapons are very sensitive, often classified, and today it's hard to imagine that many of them could be revealed to inspectors. What you have to understand also is that so far arms control treaties have only been going on between the US and Russia. So the information that they consider sensitive to one another may be different as soon as you move to a treaty, multilateral treaty where you have more partners, more nuclear weapon states, but also potentially in a treaty where you would like to give non-nuclear weapon state confidence that arms reductions are actually occurring. And in this case, you may run into issues of non-proliferation sensitive data about nuclear weapons, where there are strong legislations in most nuclear weapon states against the dissemination and the sharing of such information. So, in this case, it makes our life quite hard, okay? Because we know that very little, if any, information basically about a nuclear weapon and the what I call here an inspected item can be revealed. You may share some information, but usually that's it. You just share the information you need to conduct the inspection as expected. The problem when you're an inspector, also from the inspector perspective, is that, let's say, if you are a non-nuclear weapon state, or you try to inspect that, one of the nuclear weapon states is actually dismantling warheads, it might well be that, your competitor has way more resources than you do, which is also a reason and a source of imbalance, in your ability to bargain on how you want the inspections to be conducted. And finally, your adversary or competitor may be extremely motivated to deceive you, especially, if stakes are very high, if states continue to assume that nuclear weapons, have extremely high values for the national security, and if the numbers start dropping, they may want to be able to, keep some on the side or whatsoever. As an inspector, you cannot rule out any of this. Otherwise, the regime or your confidence in the regime will be very limited. And finally, one aspect in all of this also that I would like to touch on is that often you often expect nuclear weapons inspection to happen in the host country, in a host kind of like secured facility with inspection equipment that has been certified and okayed basically by the host. And often actually, if you bring an inspection system and you do a measurement, you cannot really go out with your device anymore. Because there are rules that say, for example, that if a computer sees some sensitive data, it itself becomes sensitive, and of course you cannot get it outside of the facility. So this makes our life again extremely hard. So developing this project is trying to address the question here. So can we come up with trusted information generating mechanisms that both protect sensitive information and are also not so intrusive? And why is that? Because often hosts will want to protect the information. They will try to limit intrusiveness, meaning they may want to limit the number of inspections. They may want to limit the number of inspectors. They may want to limit the number of facilities that are to be inspected, and so on. But on the other side, as an inspector, you want knowledge that your 3D partner is complying. You want trust in the sense that not necessarily trust is saying that you have trust in your partner, but you want to trust the outcome of the inspections. Basically, you want to trust that what you see is indeed genuine and you are not cheated, and you want access most of the time because you want to verify the object and you want to see them. So the whole game here in treaty negotiation is try to bargain between what the host wants to protect and what the inspector wants to achieve, and so it's quite challenging. And it's also challenging because when we start to think about those questions, we don't necessarily have a framework from which to play around with. And when I say a framework, it's like a way to describe inspections in a way that make them very comprehensible and effective to compare between one protocol from another. So one way we've thought about doing this is to treat inspections on the macro level, kind of like on the logical level, as interactive proof systems. So now we're going to start diving into more technicality, a little bit more mathematics and science. So interactive proof systems basically are a mathematical framework in which you construct mathematical proof as a challenge response, exchanges between a prover and a verifier. So we can think about nuclear inspections in this framework as constructing, challenge response exchanges between an inspector and a host. The inspector would say, for example, show me this item. The host, bring an item. Then the inspectors say, do measurement X, Y, and then the host do some measurements and send the value of the results to the inspector and so on. The interesting thing about building protocols is that it really helps you define also clear security assumptions, and it pushes you to justify what I will call the soundness and completeness of the inspection, which is basically word for soundness, basically making a word that the proof is that the prover cannot cheat the verifier, or at least he cannot cheat the verifier with high probability. And completeness is like the verifier, if the prover is truthful and followed the proof protocol, basically will accept the outcome. So in the case of a nuclear weapons inspection, soundness will be making sure that you you verify that you accept you accept a 3D accountable item as a nuclear weapon when it is really a nuclear weapon. And the completeness is if the host actually show you a real warhead, you want to be sure that the inspector accepted. So the challenge in going from this kind of mathematical cryptographic approach to the physical world is that you need to demonstrate that some physical assumptions actually emulate some logical layer of the protocol. And by doing so, to do so, basically, you need to discuss, fundamental physics, I would say axioms, but you also need to, basically perform the experiment and show that if you were expecting some degree of statistical distribution in your measurements, that this is exactly what is going on when you do the experiment. One thing that is very interesting here is a whole class of interactive proof systems where the prover exchange information to the verifier is what we call zero knowledge proofs. And basically what zero-knowledge proofs are, it's a way to prove a statement without basically telling you why the statement is true. So it's a way to demonstrate and to explain, in our case, why nuclear weapons is true without sharing necessarily the design information or the composition information. And I will give you some examples, toy examples, to try to wrap your hand around this. The interesting thing about doing all of this is that it shifts somehow the burden of proof, like the inspection, on the host. I am the inspector. I want you to prove me that this is a nuclear weapon. It's not me as an inspector that has almost zero resource that somehow has to come up with clever ideas so that I will be convinced. It also brings something interesting, which is the inspector plays an active role in the protocol, meaning that in some cases, he can take decisions that the host cannot predict in advance, and that will give him confidence in the outcome of a measurement. And as I say, this provides some kind of a rigorous analytical framework. Okay, so the question we can address once we went through all of this, and we have defined this, we have decided to use interactive proof. There are two questions that I think are the most interesting, and the first one is the one we'll talk today, is can we prove objects that objects are similar without learning what they are? And this is what I will talk. And another problem that is interesting is how can you prove also physical statements remotely without using standard tamper-proof hardware and cryptographic keys. In the sense that the first question asks, if I have to do nuclear weapons inspection, can the host keep it secret? And the second point basically is, if when we do inspection, can the host keep its door shut? Right. So in the first case is like, can we prove anything without sharing classified information? And the second one is, can I prove something to someone without him having to come and make the measurements in the facility where I don't want him to come? But we'll focus on the first point today, and if you're interested also by the second part, you can chat offline another time, because it's also another fascinating topic. Okay, so moving on, can we prove that objects are similar without learning what they are? And here I want to briefly remind everyone of how this problem used to be, well, is still being tackled by part of our community, is to use what we call information barriers. And the idea here is you can show that two objects are similar by making different measurements of the objects. You can make, for example, passive gamma measurements or active neutron measurements. I mean, you can think of anything. But you do all those measurements behind an engineered information barriers that basically sanitize all the data, and we make comparison between objects and then output just a single bit observation. Like saying, yes, the two objects that you're presenting for inspections are identical. No, they are not. And that's the only thing that you learn. The problem with this approach historically has been the ability of both parties to trust not only the measurement device but also the information barrier itself. It's very easy today to include, backdoors, Trojans into software or into hardware, and it's extremely difficult to verify that integrated circuits are actually doing what they're supposed to do and not are doing something else. So we decided to kind of like go away from this concept and to show that in the case where you had a trusted information barrier, which today it's really hard to actually do, another way to solve this problem is to use what I talked to you a minute ago, which is interactive proofs and interactive zero-knowledge proof. And in this case, you can build protocols so that you never really measure sensitive information. You also try to simplify the authentication and the certification of the measurement device. In our case, we use non-electronic detectors. And also, you produce much more complex observations. For example, here we're going to produce neutron bubble counts, which I will say in a minute, but which basically show how much neutron fluence detectors were exposed to. In some sense, you don't learn like a 1-bit observation like a green or a red light, but you will get much more rich observations that are interesting, because for the inspectors, it will give him more hints into what's going on if the host is trying to cheat. Okay. So moving on to a simple example. Here I try to build a toy example of how you would prove that two objects have radiograph equality. And this is relevant for our work, so this is why I'm explaining this now. So first step. How can we prove that two radiographs are identical? So here you see on the left, you take two radiographs of two items, item A and item B. You build what I would call a complement of the radiograph of item A, such that when you sum the radiograph and its complements, you get a completely flat background. Okay. So what you do here also is that you create this kind of like this flat background, such that this would be the resulting radiograph of nothing. What I mean by that is like the flat background is the radiograph I would obtain, for example, with an X-ray machine, if I were putting nothing between the source of X-ray and the film. And that flat background basically contains zero information. So when I take a radiograph of an object A, like here a big Fatman replica, Fatman Baum replica, I can construct the complements so that the sum of them actually equal this flat background as if nothing else here in the middle. If I take another item B that I claim to be identical to A, and if I provide you with the complement of A, then you can sum the radiograph of B and the complement of A, and also obtain a flat background, the same flat background. That means that the radiograph of B match the complement of A, therefore it's not item B is equal to A. Therefore, radiograph of item B is equal to radiograph of item A. Now, if I were to tamper with item B here, and you can see on the picture I removed the little kid, and if I try to sum item B on the complement of item A, then something is going to appear. Something is going to appear, and we do have a residual image here. So that's also something that is interesting in our approach, is that only truthful hosts can demonstrate that two objects are identical in a zero-knowledge way in the sense that cheating will open the door to leaking information. And often that information is sensitive, so it kind of like can act as a deterrent against cheating. So how do you make this? How we make this a zero knowledge proof? Well, let's think about Alice as our host, and let's take her secretly radiographs of what we will call a reference item, which is an item that both hosts and inspectors think are genuine. And she takes radiographs, and what she does is that she prepares complements. In this case, she prepares 2 complements of the radiographs. So as you remember, that if you were to sum them, you would get just noise, random background. And what she does is that she takes the negatives or the complements, but let's call them negative here, like easier, and we put them inside envelopes. So she hides them inside envelopes. Then she seals the envelopes because she doesn't want the inspector to be able to see the complement radiographs. Then what we do is the inspector basically decides to assign either the reference item or an item that has been declared to be identical to the reference, and he does so randomly so that Alice cannot predict in advance the decision he will take. So for example, here he puts reference on negative B and the inspector on negative A. Then we bring the radiation source. We turn them on. We verify together that they actually turn on. And then we get rid of the object and we open the envelope. Okay, so if they're both black and have like random background, that means that both objects match the negative they were exposed to. But does it mean that they actually are identical? What I mean by this is, does this mean that the inspected item is identical to the reference item? And if you think about the protocol and the steps we took, there's actually 50% chance that this is true. The reason why is that the host could have prepared 2 different radiographs, 2 different complements that would match each other to different items. And if I'm the inspector and I take the random decision to match an item against a complement, then there's 50% chance the host is going away with it, and there's 50% chance that he actually gets caught. So if the test passes, that is, we have random flat background, it only means that for the moment, items are the same at 50% chance level. So in this example, what you would do is that you would repeat the proof, and by repetition, you will increase the soundness, that is the confidence of the inspector in the outcome of the proof. And after 5 rounds, for example, you would get 97% chance that actually both items generated the same radiographs. So how do we implement this in real life? With non-electronic detectors, with neutrons instead of X-rays in this case. So here you have a graph of kind of like a graph that explains, how our setup works. So our source of radiation is a neutron tube, neutron generator that is collimated and expose a test object here that is the small space emitters. And we record the neutrons that are transmitted on the detector array behind the test object, but we also record neutrons at large angles that correspond to emission or induced emission or spontaneous emission from the test object. The detectors themselves are quite interesting here. And as I said, we didn't want it to use electronics because it is relatively easy to spoof hardware and software. So the detectors we have here are neutron detectors. They are integral detectors in the sense that they record the number of neutrons basically they were exposed to, but if you take multiple exposure, they record the total exposure. So, if I expose them for an hour or twice 30 minutes, then the exposure would be the same and the count would be the same. How do they work? There are emulsions of tiny little droplets of fluorocarbons, basically like the fluids you can find in your fridge, that is kept into a metastable state. That means the droplets are liquid, but at the room temperature and pressure they would like to be gas. So if you basically give them enough energy to move them away from the metastable state, they will basically expand into a gaseous bubble. So this is what we see here on the diagram. So on the left, we have an aqueous gel with suspended fluorocarbon droplets. And you can see some kind of like a foggy background. So those are all the tiny little droplets. They are about like 100 micron in diameter. And then you see macroscopic bubbles that resulted from neutron interaction. The interesting thing here is that they are only sensitive to neutrons above a certain energy threshold that is required to create the macroscopic bubble. And also they are insensitive to gamma rays, which means that the measurements really is here just about neutrons. And interestingly, neutron measurements often carry much less information than gamma measurements. Okay, so same as before, how do we try to prove that two objects are equivalent or not equivalent? Well, we take basically what we do is like we take radiograph of the test object on the bubble detector array. And so here you see pixelated radiographs where each pixel actually corresponds to the bubble count of a single bubble detector. So here, for example, if you were to take a radiograph of a valid item and sum it onto its complement, so that the sum is random background, and you will build the complement so that the random background that is obtained at the end is equivalent to doing the radiograph of the valid doing the radiograph for the same exposure with no object in the middle. So this is how we obtain the zero knowledge property. So if you build the complements this way, when you take the radiograph of valid item, you end up with Poisson noise that is just background measurement of nothing. And the interesting things with Poisson distribution in mathematics is that they sum very nicely, and they do not carry information in this case, not only in the measurements, but also in the noise of the measurements. So which makes this test zero knowledge. So then if you were to take the radiograph of a spoof item, so here, we remove the ear of the small space emitters and had it on a valid complement, inspectors, what they will see just what is on the right, which is random background that with 3 points that are basically outliers to the expected distribution of counts for a valid item. So in this case, using statistical tests, you would just say, okay, this is not a valid item, something is fishy. So in this case, you could retest or not even retest because it's so unlikely that this is happening that it's very possible that the host was cheating. Okay. So in our protocols, of course, we are trying to show that two objects are identical. One, at least, well, actually, two objects or many objects, maybe 100 objects. At least one of them we believe is a true nuclear weapon because either we took it off from a delivery vehicles, or just 100 items were presented to us, said that they were, and the host claimed that they were nuclear weapons. And maybe after we prove that they're all identical, we randomly put one of them onto a delivery vehicle. But the idea is this is a way to show that something that is declared as a nuclear weapon is a nuclear weapon. Which means that we're trying to do a proof of physical equality between items. But what the system does, the system we've been building so far, is doing a proof of radiographic equality. And of course, sometimes, depending on the neutron energy at which you take the radiograph, you may not be able to distinguish different materials that would have the same opacity if you just do transmission measurements. So, for example, if I have an object that has 50% opacity, I can add 14 emitted neutrons. I can probably build another object that has the same opacity. So how do we get to the point where we claim, physical equality from radiographic equality? Well, it's by taking multiple radiographs at different energies, and at different energies of interest that give us information in transmission and emission of the object, like their configuration, their geometry, for example, the presence of IZ materials, what's their K effective, so that their ability to produce neutrons from fission, what's their configuration in low NIZ, what's their isotopic composition, and all of this we can actually probe the object to ask those questions by using neutrons at different energies. And in particular, we're interested into, so 14 emitting is nice because it's easy to use, it's rather penetrating, and we're also interested into the hundreds of keV energies. So here, if you can see the cursor, the proton lithium source or americium lithium source, but more likely proton lithium source, that where the cross section for fission, for example, between uranium and plutonium isotopes is very different. So, for example, you can make sure that if I have two spheres of uranium, for example, you can distinguish their isotopic composition. And so you build all of this into a protocol where you expect the distribution of counts that you see in your bubble detectors at the end, a function of the object orientation, the interrogating energy, the detector energy threshold, and the level of statistics that you feel is required for the inspector to be, happy with the measurements. What I mean by that is you want, do you want to make the difference between uranium at enriched at 20% and uranium enriched at 93% in the 235 isotopes, or do you want to see a difference in enrichment, let's say 0.8 versus 0.81, you know. So all of this will depend on your level of statistics, which here in our case translate into the maximum number of bubbles, and then you can count in one of those detectors. So those detectors have tens of thousands of droplets in them, and so far, you know, we make measurements where we count hundreds of them. So right now we're building system where we can count, you know, thousands of bubbles, so as to increase, I don't know, our level of statistics. Okay. I will wrap up pretty quickly now. Here, I'm just going to show pictures of our setup here at the PPPL lab. So instead of doing a gigantic 2-day radiographic array that Alex envisioned first in his first paper, I tried to simplify my life and just did 1D, you know, line radiography of objects. So here in the center, I would put cubes of different materials and take a radiograph of them. So in practice, you see, I basically build this gigantic collimator from where you get 14 emitted neutrons, and those then take radiographs of the cubes that I align carefully in front of a line of 7 detectors. Then what I would do is I would hide the detector pattern under a black box, so to simulate that, you know, inspector would not be able to see what's going on there. So why did I pick this weird arrangement of cubes? So, you know, aluminum and stainless steel here. This was to make a proof that I could confirm that if I try to tamper with the cube pattern, I would be able to see it, and if I were to inspect twice the same pattern that is here, which is my reference pattern, I would not learn anything about that pattern. Like, I would not be able to know what was the materials and what was the arrangement. And so 1 aluminum cube corresponds to, those are 2-inch cubes, gives you basically 25% opacity, 2 aluminum cubes 50%, 2 stainless steel cubes 75%. So this is why I picked those number and this arrangement. So what happened when you do the experiments? And so what I mean here is I take, you know, the reference pattern. I took many radiographs of it. I create the complement image of this radiograph that I load onto the detectors before I do an inspection, and then I bring the item to be inspected, and I take his radiograph that I sum with this preloaded pattern, so that if the item is valid, then I should see nothing. So here you see that 5 different cases. One case is like I present a valid item, and those are the blue dots. I expect a Poisson distribution centered on 1200 bubble count, and I basically see that indeed there is nothing, and that it's the noise is from statistical. The noise is just statistical noise. Then I show a dramatic example of what happens if I take the radiograph of the inverse pattern on the complement of the valid radiograph. Then I get this gigantic, you know, a very low count on the left where it's very opaque, much more opaque than it was supposed to be, and a lot of count where it's much less opaque than it's supposed to be. Then I just take the valid pattern and I add a steel cube on the left, and I can see that there's a drop. Then I try to remove materials on the right with number 3, and I see also an increase in the number of bubbles. And finally, I just replace the steel cube by aluminum, and it's much harder to see visually, but if you run the statistical test, you would reject that. But here is an example of what I mean by the level of statistics is that the more bubble we would be able to count in a given inspection, the easier it would be to distinguish smaller and smaller changes between a true item and a spoof. Okay, so aluminum and steel are nice, but you know, people don't take you seriously until you actually make measurements on uranium. This is what we learned recently. But this is also why we were very fortunate to participate into experiments this summer at the former Nevada test site, where we went to the device assembly facility to make measurements on a sphere of almost 14 kilograms of 93% enriched uranium. And that's actually, the sphere is formed from nested small, you know, nested hemispheres, so you can remove materials from the center. And here we wanted to see if we could distinguish this removal depending on, you know, what was the neutron interrogating energy and so on. We had very interesting data that I'm still crunching right now, but it looks pretty good. Like, for example, with 14 emission neutrons, we would see that some uranium was removed from the center of the sphere in just a 2-minute irradiation. Okay. So where are we now? Well, in terms of experimental demonstration, as I said, to go from radiographic quality to physical equality, you need to test the system with various neutron energy, and this is what we've been doing. And so we've done a lot of computation already, and we've done some experiments, including with HEU. What we would like to do is to do some measurement with proton lithium beams, but that's kind of like rather a little bit more complicated system, because it's you need a cyclotron to accelerate protons, and we don't have this right now at Princeton, so we're looking for partners. And we also would like to make some measurements on plutonium. So I'm just going to wrap up now because I see that I'm way past the time limit. So just to conclude here, so what we were able to prove so far is that it's possible to compare two physical objects, without learning what is their geometry and composition. And so this is very helpful if we want to build an inspection system that would compare items that are declared to be nuclear weapons with each other to prove that they are all identical, but furthermore that they're also identical to items that would be, for example, deployed on delivery vehicles. Finally, we've also made measurements on HEU, and what we plan to do in the future is to increase our statistics, make measurements on spontaneous emission, design also a field version of our experiment. So I've been traveling to all of this to Nevada, and it was quite an experience. And so what I'm interested now is to say, you know, I'm not going to design a portable version now, but I want to explore how this could be implemented in real life, and I would like to do this with Tamara's pattern, system, where she's developing a virtual reality environment where we can try all our crazy ideas. And finally, the thing I would like to tackle a little bit more is what we call, this initialization problem. So where do we get reference items from? And what I mean by that is, like, where do we get items that we believe mostly are nuclear weapons, without having to blow one off, basically. Yeah. So that's it. Thank you very much for your attention. And I hope I was clear enough. It's hard to give this talk when I don't see, the eyes in the audience going, big or small, if they're actually understanding what I'm saying or not. But thank you very much. And if you want more information, don't hesitate to get in touch with me.
Okay, thank you. That was very interesting. I had a couple questions, and we'll see if anybody else wants to weigh in. How long will the bubbles last in the detectors? I mean, is this something you can store for a long time?
Yes. Yes. So the question is, how long the bubble lasts? So the bubble themselves reach an equilibrium size, and then they last. They last forever.
Oh, okay.
They last forever unless what you can do is you can recompress the detectors. So this is why we don't throw them away. You can put them into like a water chamber and you increase the pressure, and that will recollapse them into droplets.
But they're stable to sort of ambient temperature.
Yes, absolutely.
Yeah. And how do you count the bubbles?
So
you're talking about potentially up to 10,000 of these things.
Yeah. So so far we've done this. In our experiments here, we've done this optically, but by taking pictures of the detectors and counting them with software. We build also a system here that takes 360, and we're still building it actually. Well, we build it. We have to check the software now, but that takes 360 degree movies, to track more and more. But eventually, you can think about. People have been using MRI, for example, this kind of things, to have a perfect 3D reconstruction. Yeah.
Okay.
But you can count them by hand also.
Yeah, no, that's what it sounded like at this point. The other thing I wanted to ask you, so part of the process you're talking about here is the technology, but it's also partly the sort of gaming or the interactive procedures. And I'm wondering whether you've set up simulations that assumes the technology works to see how the actual interactive process goes. Have you played out some of those games?
I haven't yet. I'm actually very interested to try it. And the reason why is I want to understand when you give the opportunity of an inspector to actually take a decision that matters, how does this influence interest in the outcome? So what I was thinking to do is now that I've got all this data, you can already play tabletop, exercises, where you could when you could have the inspector say, okay, I take this decision, and you say, okay, this is what you see, how does this influence your judgment? And potentially we could actually also play real inspection with our setup at Princeton, which we thought to do, but then we say if we're playing it just with ourselves, then no one is going to trust the outcome. So we have to think about this, yeah. But we could do so, yeah.
Yeah, it would be interesting to see if there are things you hadn't expected that come up when you actually have a, antagonistic inspector. So. And the last thing I wanted to ask you was, you were talking about using different energies to try and inspect these things. And how many different energies, you talked about two here, but how many different energies do you think you would actually want to use in a real system?
That's a good question. I think that for the moment, if you have two active interrogation plus one measurement that is just from passive emission, I think with those 3 data points, you really constrain the problem already pretty far. So then the question, and this is still something that we're working on. Do we need more than 3? Or is this enough already? Yeah.
Okay. I don't see other questions. It's after 1, so I think we'll end here. Thank you for doing this. I have been in contact with the MIT group to see if they'll give a talk sometime in the near future about their alternative way of looking at this, and so we'll try to set that up within the next month or two. So
That's
again,
great.
yeah. So thanks again, and we'll look forward to seeing the future of this work.
Great. Thank you.
Thanks, everybody.
Thanks, everyone.